Syzygy, episode 60, Big Moons. And welcome back to another edition of the Syzygy podcast. My name's Chris Stewart. Sitting opposite me at the table in her office, as ever, Emily Brunsden. Hi, Emily.
Hello, hello.
So today we're talking about moons, specifically big moons. Well, there's been a few recently.
Yes, and there's going to be some more.
Some more. So we've had a few big moons, and there's going to be more big moons. And we've talked about moons on this podcast a few times now. Arguably too many times for only one part of the universe. I mean, a fairly prominent part in the night sky.
Well, it's a big bit in the sky, isn't it?
It is big, but it does kind of make me wonder, like, surely, sometime soon we're going to run out of moon-related stuff. We're going to run out of lunar topics for this podcast. Apparently not, because we've got a load of big moon stuff to talk about today. Emily, what's going on? What's with the big moons?
Big moons. So we're going to see across the first half of 2020 a bit of a resurgence in the popular press about supermoons.
Was it this time last year you suddenly became Moon Girl? On the popular press locally and even nationwide, it suddenly, hey, let's talk to Emily about supermoons, because there was a string in a row of weirdly named moons. And that's astronomy, apparently?
Well, not exactly.
Not really?
But it turns out that if you do want to get someone into your, press article that's going to talk sensibly about moons, astronomers are a good place to look for.
Well, I mean, it does immediately come to mind. It's either astronomers or astrologers, and we'd rather the former than the latter. So just remind us, what were some of the things that you were talking about sort of 12 months ago? There were some weird moons.
So, yeah, we had some of the moons that are actually going to make a resurgence again this year.
Okay.
So I think we had 3 supermoons in a row last year, and this year we're going to build on that. We've got 4 supermoons in a row.
4 in a row?
4 in a row. So we've already hit one of the 4. So
what have we had so far?
Last month, on February 9th, we had the snow moon.
Never heard of that one.
Now, well, it was in the suite last year as
was
well.
it? Okay. I must have missed that one. I must have still been asleep.
Yeah. I mean, we'll get to a definition of what a supermoon is later, but you'll often see these moons called as things like super snow moon.
So just to be clear, we've had a snow moon, but we haven't had a super snow moon?
We've had a super snow moon before, but the actual word snow has very little scientific meaning.
You stagger me with that. I'm absolutely amazed to hear that that's not really astronomically research-based.
No, and it's something that I'm not really super comfortable even as a human, because I do. Okay, so the names of moons, the names of the 12 or 13 full moons in a year there is some claim that these names that are commonly used come from Native American tribes.
Okay.
Now that already starts to ring alarm bells to me personally, because I'm no anthropologist by any stretch of the imagination. But first of all, there's a huge diversity of peoples that were living in North America.
Yeah.
And whether even these people would agree that these are the names. When I looked up, for example, the snow moon, I also got names like the hunger moon, the storm moon, and the chaste moon.
Okay, so I guess you could argue it the other way and say, yep, snow moon, perfectly legit, but so are all of these other terms that we could use interchangeably for exactly the same phenomenon. So let's start with that one off the bat. The snow moon's the one we've had this year?
The snow moon was in February.
And that was what?
That was a super moon.
Okay, but why a snow moon?
It was in the month of February.
Right. Okay,
Yeah.
So being absolutely clear here, a snow moon is a full moon.
In the month of February.
That's it.
That's it. Yeah.
That's all.
That's all.
Right.
So you get
okay.
you get a snow moon every year.
Right.
If you believe in a snow.
I can see how astronomers might not get particularly excited about this. There's not a lot of research grants going for full moons in the month of February. Like, it either is or it isn't, and you don't get a lot of funding to research that one.
And it's not particularly universal either, because anyone in the Southern Hemisphere will look around and say, snow? Yeah, what?
Yes. Beg to differ. Yeah, depending on where you are, it's either really hot or your entire country's on fire. Either way, not a lot of snow going on. Yeah. Okay. So snow moon, we've had. That's full moon, month of February.
Yep.
What's next?
So the next one's in March the 9th. There's full moon, which is also a super moon.
Yeah.
This is called the worm moon by some people.
Because it's in March.
Because it's in
And the
March.
worms come out in March because it's spring.
Maybe, but
If you've
equally,
got a big compost pile full of worms, it's a worm moon.
I saw a worm months and it wasn't March, so I don't really know.
Okay. But the
but
worms get that one.
You could also call it the crow moon, the crust moon, the sap moon, the sugar moon, the lenten moon, or the chase moon, which some of those overlap with other months.
Yeah, I was about to say, surely it wasn't February chaste.
Well,
March is chaste as well.
yeah, this is the thing. You try and create a system which is maybe based on parts of some culture, then
That's very generous calling it a system. I don't think this is particularly systematic. And I mean, just chaste. Like, hang on, we're coming into spring. The whole thing about spring is fecundity and nature basically saying, get it on. And it's chaste? Really?
look, if this is the reason you need not to live your life by astrology, then go for it.
This was the final nail in the coffin. I was totally with it until we got to the chaste moon. And I said, no, throwing all my astrology books out the window to be eaten by worms. Okay, so that's next then is March and the worm / everything else moon. And after that?
We got April the 8th, commonly going to be called the pink moon.
Because it's going to be pink?
There might be some pink flowers out during April.
That's as good as you get?
I think so.
Come on, there's got to be a reason it's a pink moon.
Well, it doesn't actually change colour. I'm going to put that out there now.
I was guessing that. I mean, that would be fairly extraordinary. Like, that would be worth a research grant, I think, if you were able to conclusively show that in a couple of months' time, the moon's going to be pink for the following astronomical reasons. I think that would be awesome. But no, it's just called that. Okay.
But if you really want, you can also call it the sprouting grass moon, the growing moon, the hare moon, the Pascal moon, the egg moon, or the fish moon.
The egg moon. Wasn't that a Beatles song? I am the egg. Never mind. Okay, but that's February, March, April. We've still got one to go.
And one more is May. So May the 7th will be the next full moon, also a super moon, also called the flower moon by some people.
That's it? Just the flower moon?
Moon.
Right.
Flower as in the plant.
Right, not as in the baking
No.
stuff. Right. Okay. All right, so that's
actually, calling it the flower moon in terms of the baking stuff might even make more sense because the other names I found for it are also called the corn moon or the milk moon.
Right. Okay, on a kitchen theme.
Yeah, so you could get some pancakes going.
You could.
With your egg moon, your
based on
moon.
last episode's theme. Yeah. Okay. So we've got 4 of these specially named moons in a row, which is either exciting or annoying, depending on which position you're coming from and how close you are to the astronomical community. But they're all supermoons. So
Yes.
we probably should have a bit of a chat about that. I think we have talked about this on the show before, but Emily, remind us if we have or if we haven't. What's a supermoon?
Okay, so I did actually dig a little bit deeper into this time. I mean, we've always known that the supermoon is a full moon that appears to be slightly bigger in the sky because the moon is actually a little bit closer.
Right, and this is because the moon doesn't go around the Earth in a perfect circular orbit, that sometimes it's a little bit closer and sometimes it's a little bit further away. And so when it is closer and a full moon, then that's a supermoon.
Yeah, but so I actually found the proper definition of a supermoon, and then we can talk about the astronomical sort of flip side of this.
Okay, well, it's nice to know that there is a proper definition after all of the preceding 10 minutes of discussion about things that have absolutely no proper definitions.
Well, take proper a bit lightly here because this is an astrological definition.
Okay, Oh, I just feel this episode spiraling down already. But okay,
Yep.
proper with air quotes around it. Go on.
So in 1979, astrologer Richard Knoll decided what the definition of a supermoon would be.
Good.
And that's defined as a moon which is full when it's within 90% of its closest approach to the Earth.
All right, well, I'm okay with that. That sounds like a reasonable definition to me.
Yeah, it doesn't really have any significance at all astronomically. The 90%, why choose 90? Why not choose 95? Why
Sure.
not choose 85?
But I mean,
why not choose 10?
if you have to choose a number, choose a number. Let's call it 90. Fine.
It's also applied sort of fairly ad hoc across the internet, at least as far as I can see.
Mm-hmm.
So, for example, I found 2 different actual numerical definitions of this. So the websites timeanddate.com use a definition of when it's closer than 360,000 kilometers.
Okay, and does that overlap reasonably with the 90%? Who knows?
Well, yeah, kind of.
Sure.
It seems a bit rounded to me.
Okay.
Although Sky and Telescope use a definition of 358,884 kilometres.
And what was the other one? 360?
60,000. So, maybe they're just,
It's fairly close.
rounding errors. I don't know.
It'd be nice to know that people had decided this. On the other hand, it's so non-significant that it probably really doesn't matter. Is it a supermoon? Is it not a supermoon? Sure. Who cares?
Yeah,
But,
well, this is the
okay.
thing. A supermoon is nothing special, really.
Yeah.
I mean, it is nice to
The
know.
entire astronomical community just shrugs.
Yeah.
Sure. Okay.
So what astronomers do actually care about when it comes to the orbit of the moon and relative, distances to the Earth, you have two different points in the moon's orbit that we keep track of. They're called perigee and apogee.
And what are they?
So perigee is the point at which the moon is exactly the closest to the Earth in its orbit. And at that point, it's 363,229 kilometres away.
So that's its closest point.
Yep.
Yep.
It's perigee. And apogee is the opposite of that when it's furthest away. So that's when it's 405,400 kilometres
Okay.
away.
That is quite a significant difference.
Yeah.
Yeah. Okay.
A few percent. So these are those things that astronomers do know. And actually, I got quite excited by this because it turns out you can calculate a lot of things about the moon's orbit, and this is the real astronomy. And so a lot of these calculations and terms actually come from very, very distant past where astronomy and astrology used to kind of mean the same thing.
Right.
So when we say words like perigee and apogee, and it sounds like I'm going to now tell you that it's a good time to buy a new business, that's not
The moon is in the
coincidental.
seventh house, and it's a really good time to trust in your friends. And yeah.
Yeah.
Yep. Okay.
But the words themselves are still relevant scientific
Sure,
words. And,
sure.
being aware of the moon's orbit is really important scientifically. We want to know very, very precisely where the moon is when it comes to looking at things like satellites, because the moon's orbit affects them gravitationally. Of course, if we want to go to the moon, we need to know
Yep. That's
pretty
useful.
accurately where it is.
You need those calculations to be closer than, a couple of tens of thousands of kilometers in order to get into the right orbit and not crash into the surface of the moon or miss it entirely. Yep, that's
Yeah,
really quite
equally.
useful.
And we also use them for things like predicting eclipses and those sorts of
Yeah.
things, which is actually a really, really tricky mathematical thing to do. It sounds like it should be easy, but it's actually pretty hard.
I could imagine it probably is. I mean, on the face of it, it sounds fairly easy. When does the moon get in front of the sun? And, how much is it going to be in front of the sun and so on? But actually, you're dealing with a very tricky three-dimensional problem involving three different things in non-circular orbits. That's very much, as we say in the sciences, non-trivial.
Exactly.
Yeah.
So, well, here's where I got really excited and
Okay.
started doing a bit of the astronomy in terms of the moon's orbit. And the first thing you might want to know if you're going to calculate the position of the moon's orbit would be the definition of a month.
Funny, one of those things that I'd never really considered needed a definition. Like, you just look at the calendar, don't you? Having said that, we'd all do know that the calendar is a bit of a weird thing, and we've got some months which have 30 days and some which have 31 and one which has 28 or 29 depending on the year for no apparent reason. But other than that, I kind of would have thought a month is just what we call it. So there's a definition.
There's more than one definition, in fact.
Excellent. Good.
There's at least 8 or 9 that I've found.
8 or 9 definitions of a month. Go on then.
We'll talk about 4.
Okay,
Just
just-
because these are the most common ones.
Because the
that
other
you
4
mentioned.
are ridiculous. So, all right.
Okay, so the first one you might want to think about is what would be your astronomical hunch of definition of what a moon's orbit is, or what a month is, sorry.
What a month is, it's pretty close to the 28-ish days of a lunar cycle, right? So that's got to be related. A month surely is the moon going around once.
Okay, so you want to define a month by the time it takes for the moon to orbit the Earth once
Let's say yes.
and return to its original point.
Yeah.
Okay, very good. This is called
I can see I've just walked into a trap, haven't I?
well, not really.
Okay.
This is called a sidereal month. Mm-hmm. And it's, as you say, at the exact time if the moon's going to return to the exact position in its orbit relative to the background stars, let's say. So it's going to return to the same point in the constellations. So this whole sidereal month is actually 27.32 days. Mm-hmm. It's not what you might think of as a month when you look into the sky, though, because it's very different from the month where you might see the phases of the moon change from full moon to full moon.
is that because the definition that we just talked about is against background stars and so on, but in that intervening time, we've just gone around the sun a little bit and we've turned a bit and so on. And so even though the moon is back to where it was in the sky relative to the background stars, we're not where we were, and so things are going to look a bit different.
That's exactly right? Yeah. So the
I'm
next
learning things.
definition you can have of a month, which is quite useful. This is kind of a more human definition, you might think, because this is the synodic month.
Synodic.
So this is the time you have from full moon to full moon, or new moon to new moon. Right?
Okay, so that's another good definition.
Would have been what ancient cultures, for example, would define as a month, right? And so this is 29.53 days.
All right. So that's a couple of days longer. Okay. And those couple of days come from the aforementioned, we've just gone around the sun a little bit. And so the direction that the light's coming from, which is what makes a full moon, is slightly different. And so we're adding on a couple of days there.
Yeah. So the moon has to travel a little bit further to get back to the point where it's illuminated the same way by the sun.
Okay. Yep. That makes sense.
So, yeah. And now that particular 29.53 days is not exactly precise because it turns out that the Earth orbiting the sun is not perfectly a circle.
No, so the moon's going around the Earth in not a circle, and the Earth's going around the sun in not a circle. And so from month to month, the differences per month changes. Ow.
So one way to think about it is that when the Earth is a little bit closer to the sun, it's actually moving a little bit quicker in its orbit. And when it's a little bit further away from the sun, it's moving a little bit slower. So the amount of distance it covers, the Earth covers in its orbit around the sun changes, which changes how much the moon has to catch up.
Yeah, I can see that. Okay, so at different points in the Earth's orbit, then the time from full moon to full moon will be different. Yeah. By how much? How much does that change?
About 3/4 of a day.
Wow. Okay.
So 18
That's
hours or
quite
so.
a lot.
Yeah. So we do have to keep that in mind when we're doing our calculations as well.
Yeah. Having said that, though, 3/4 of a day across a sort of roughly 28, 29-day period, it's significant, but it also shows you that the Earth's orbit is quite circular.
Yeah, we are very, very close to
we're
being
not
circular.
far off from a circular orbit. Like, it's not like, some months are 4 days long and some months are, 50 days long. It's really quite close to 28, 29 days.
Yeah. But you can see now why we don't exactly have the same number of full moons every year. Some years we have 12 full moons and some years we have 13.
Right.
And that's because you can't divide your 365 days of a year exactly into these numbers.
Yeah.
And you get a whole number.
Yeah.
Back again.
That makes sense. It's not quite as clockwork a universe as we perhaps once imagined.
So it's a bit annoying that we can't have the same number. If we want to have an astronomical definition of a year, the astronomical definition of a month doesn't quite work.
Sure, but I mean, why should astronomy be any different from any other branch of science where it's messy in the real world?
It is very, very messy.
Yeah, okay. So that's two definitions of a month. One is when does the moon get back to where it was in relation to the fixed, even though they're not particularly fixed, background of stars. And the other is when do we get back to full moon from a full moon again? Okay, That's two.
Okay, so the third one's slightly more complicated. Now, we've got to imagine the moon's orbit as an ellipse now.
Okay, not a circle, it's an ellipse.
Yeah, so we have this perigee and apogee.
Yep.
Now, those positions of where perigee and apogee are change over time. What you can imagine is the whole ellipse rotates around the Earth.
Okay, so it's the moon's moving in an ellipse, not a circle, and that ellipse itself is rotating around the Earth. So it's like, going in an ellipse, and then that ellipse slowly but surely turns.
Yeah,
around.
So sometimes perigee is close to the sun, sometimes it's on the opposite side of the Earth to the sun.
Yeah, which is why we don't always have supermoons when it's a full moon. Sometimes we have a supermoon, and sometimes we have it that the moon is at the average distance, and sometimes we have it that the moon is really far away, or a bit further away, because of that rotating of the ellipse. All right.
Yeah. So that whole ellipse takes about nearly 9 years to go round.
Right. Okay. That's quite a long time.
Yeah. So it's precessional. So this is in the same way that we have precession in all sorts of orbits. We have precession of the Earth's rotation axis as probably the most famous example.
Yeah.
So if you drew a line out from the top of the Earth, of its spin axis, and looked at what star that is, at the moment that star is Polaris.
The North Star.
The North Star, from the top anyway. We don't have a bottom star.
No, sort of a bit of a void, really, isn't it?
A bit annoying. But that will change over time, and that's because this precession of the spin axis of the Earth changes over,
Right.
I think it's 26,000 years or something.
Yeah. So we've got a little while to wait before Polaris moves out of the northern pole. But you're saying that the same phenomenon, the same physical phenomenon called precession, is what's behind the ellipse of the moon's orbit, slowly but surely rotating around. And is that why? Because it takes 9 years, you said, roughly. Is that why we've got so many supermoons happening now? Is because we're at a point in our orbit and the moon's orbit and the precession of the moon's ellipse, so that full moons are all happening close to us.
Yes.
It's that sort of convergence of all of those things.
Yeah.
Right.
Although remembering that supermoon definition is fairly arbitrary.
With the air quote version of the definition,
So what happens with this in terms of the length of a month is it does actually make our months a little bit longer. So instead of being the 27.32 days, which we had for the sidereal month, this makes them up to 27.55 days.
Right.
So a little bit of a change.
Okay. All right.
So that's fine. Now we've got a fourth type of one, and this is to do with the moon's orbit relative to the equator of the Earth, if you like, or the ecliptic plane.
Okay. Yep. Talk me through it.
Okay, so the Earth is going around the sun. Now we're a little bit tilted over, which is so our equator doesn't line up with the equator of the sun.
That's right.
But
that's why we have seasons.
Yeah.
That's where that comes from.
But we draw this imaginary plane, which is the Earth's orbit around the sun, and this is the ecliptic. It's the plane that most of the planets pretty much orbit in.
Okay.
Right. Now the moon is tilted to this plane, so it doesn't follow exactly the Earth's ecliptic as it goes around. It's tilted by not a super huge amount. It's about 5 degrees.
Right. So it's not a lot, but non-trivial.
But what this means is you get two important points in the moon's orbit called nodes.
And I'm going to guess that's where it crosses the ecliptic.
Yes.
Hey!
So you get a point where you get an ascending node. It's like when the moon comes up into the northern celestial hemisphere, and you get a descending node. And then it goes back down again.
Okay, so just picturing this in my mind then, I'm imagining a plate, or we want to go back a couple of episodes, a pancake, which is the solar system, flat. That's what, let's say for the sake of an argument, all the planets are orbiting around the sun in. So it's nice and flat. And then the moon going around the Earth, if it was on exactly that plane, it would be going around on that same level, just on the surface of that pancake. But it's not. It's tilted slightly. So for some of the moon's orbit, it's ducking down below, and then it hits a node and comes up above, and then ducks down below and comes up above. And every time it crosses, that's a node.
Yeah.
Okay. And therein lies another definition of a month.
Yeah. Now, those nodes were known since very ancient times for astronomers. Astronomers have been doing these maths calculations for a very long time.
Yeah.
And they were thought, I'm not sure exactly what the link was, but there was something to do with dragons.
Well, it has to be. Yeah. Makes sense.
So this is called a draconic month.
Right.
And this is used by using those nodes, using how long it takes for those nodes to return to the original points and or to rotate around. And that whole period that it takes the nodes to go around is 18.6 years. Mm-hmm. So that gives us a draconic month, which is interestingly shorter than the other months. This is the shortest month of all. It's 27.21 days. And the reasons why it's shorter is because the nodes are moving around the opposite direction to, say, the moon's orbit.
Okay, I'm going to take your word on the maths for that one. Yeah, sure. All right, so we've got anything from 27.2-ish up to, what, 29 point something. So somewhere in the middle there, around 28 days is the average. Can you take an average? Is that allowed?
Yeah, although you might not had the same number of days. Well, if you want the same number of days in a month, then you're going to have to have days which are not night
I guess
and day,
that does
and
kind
it gets
of
very complicated.
It is really interesting that we have all of this, and there's another 4 we haven't even talked about.
Yeah,
you found another 4 definitions of month. At least
there are more than 100 different perturbations to the moon's orbit.
It does kind of does beg the question for me, which is, do we care? And do we need a definition for a month? We clearly don't from a calendar point of view. Like, it's not like on the basis of this information, we're now going to go, oh, well, we're just going to throw March out, that doesn't have that number of days anymore. We're going to go with 27.2 or whatever we choose. Because that's ridiculous. That's not how the world works. We work in a number of days, and it's just a calendar. It's just a convention. Fine. We don't even need months or weeks. We could just do whatever the hell we want. Do we need a definition of a month, or is this turning it around and just saying we can measure these intervals? And so if we're interested in nodes, then we're talking about 27.2 days. If we're interested in this, then we're talking about that.
Well, we do need to know this information, and we need to know for not just scientific reasons, but also cultural reasons as well. So as you'd say, okay, our whole calendar it kind of works, and normally you probably haven't thought about how actually the whole calendar is just a thing that happens, and the months are there and they do things
until you have to remember, does this month have 30 or 31 days, and then you have to go through the little thing in your head. But other than that, no.
But this modern calendar is relatively new, and lots of cultures had different ways of making up their calendars that were based on astronomical observations, and we need to know very precisely what the moon was doing in the past if we want to marry up kind of dates and things between even very different calendars that were happening in very different parts of the world.
That's a good point. If you're looking back historically and saying, okay, well, this thing has been written down or carved in stone or told through oral tradition in this way, and we've got a date on that. The trouble is it's not based on our calendar. How do you match those up without an understanding of, how did their calendar work? And if that was based around a particular definition of a month, which was based on astronomical observations, that makes sense.
Yeah.
Sure.
And this propagates through to even relatively recently. I mean, even in the last 100 years or so, we have had different countries using different calendars. So you've got to understand very precisely how these are built and what the actual astronomical observations they were made from were doing.
That makes a lot of sense. I'd never thought of that before, but that's a good point.
So, of course, that's very important culturally. Astronomical observations are very important as well. When you talk about things that were happening in the night sky, things like the lunar phase were recorded, the angle of the moon in the sky. And if you don't understand the subtleties of the moon's orbit, then you don't actually have a clear idea of what that date might be if you need to backtrack.
It's not particularly interesting to look back through history and go, well, when did they have a full moon in, China in the year 10,004? Or 1004. That's probably makes more sense. But things like supernovae were observed. There are historical recordings of big bright light in the sky that you could even see during the daytime at this point on our calendar. Well, it'd be kind of nice to be able to pinpoint that. But to do that translation, again, you need to know what their calendar was talking about.
Yeah. So that's looking backwards. We also want to look forwards, of course, and for the reasons we've already mentioned, you want to know where the moon's going to be at particular times, because often you're planning missions to particular objects, including the moon, decades behind where you're actually planning to launch and do these things. So it's good to know. It's maybe more important, you would argue, for the planets in the solar system. If you want to go to Mars, you've got to know when the windows of opportunity for Mars are, et cetera, et cetera.
Yeah. You kind of got to start your planning of your mission there, because there's no point in launching unless you're going to actually end up at the planet, which is a very long way away. Yeah, that makes sense. So I can see how all of that comes into the calculations. And it is really important, valuable stuff. I just never thought about it from the point of view of, do we need definitions of months? But I guess from the point of view of, well, we need to be able to talk about these kinds of time periods, these kinds of spans, these kinds of events, astronomical events. When is the moon going to be in a particular position or in a particular phase of its orbit? And what do we even mean by that? Then you actually have to start talking about, no, what we're talking about is this sort of thing, not that sort of thing. Makes sense.
Yeah. So the net result of all of this is that when the moon is close to the Earth, because of all these various perturbations to its orbit, and when it is at perigee, it's about 14% bigger.
14% bigger. So a super full moon would be 14% bigger, like a proper one, like an actual.
Yeah,
this is as close as it gets. Astronomically super, right?
Yep.
14% bigger in the sky.
And something like 30% brighter.
Okay. 14% bigger, that's in terms of area. So in terms of its...
that's in linear size. So that's just like diameter.
Okay. Yeah. All right. So it definitely does look bigger. You could, if you compared side by side, you could do that.
Yeah.
You could spot that.
You're right. If you took a photo when it was at
Yeah.
its smallest and when it was at its biggest, you could definitely see a change of 14%.
However, the moon's actually quite small in the sky. Like,
Yeah.
it feels big, but it's not. If you go and look at a full moon and just actually pay attention, it's very small in the sky. It's like the size of the thumbnail out of the distance of an outstretched arm. Like, that's small. Could you really tell that it's a supermoon just by looking at it?
I would argue you can't.
Okay.
If the only way I would maybe consider you were telling me that you could observe a supermoon by eye would be if you were able to measure the brightness change with your eyes.
Yeah,
and that
okay.
takes a lot of training and a lot of work to do. Some people can do it exceptionally well.
Did you just say a second ago what the difference in brightness was?
It's about 30%.
So that is quite a lot.
So that's more significant, and that is
Yeah.
because the area is bigger.
Yeah, call it
So-
a third more.
Yeah.
Yeah. Okay, so that's possible. I'm just trying to think. The back of my brain was just doing a little. I wonder, how would you do that experiment? Like, could you lock someone in a cupboard for a while and then take them out when there's a full moon, so that they didn't have any external influence on whether or not they knew it was a supermoon, like they haven't seen any headlines or anything, and then take them out and then ask them? I don't think you'd get ethics funding for that.
No, I wouldn't like to write the
But it would be
proposal
fun
for
to
that.
try. Anyway, okay, so 14% bigger, 30% brighter.
Yes. Nonetheless, there are lots of different full moons, whether they're supermoons or not, that lots of people have asked me, is the moon a bit bigger at the moment?
Ah.
And there is a real, and it's a very, very well-studied effect whereby the moon does sometimes look bigger, particularly if you see it near the horizon.
Yes. Now, this comes up a lot. I had this conversation with one of my daughters not that long ago, and the number of people over the years who adamantly, absolutely, foot-stompingly, table-poundingly affirm that the moon is definitely bigger when you see it closer to the horizon. If you see a full moon when it's fairly low in the sky, it is huge. And that's, like, they're not making that up. That's real.
It's real perception. I mean, you know deep
It
down.
looks real.
You
It
know deep
seems
down that
real.
the size of the moon does not change from when it is on the horizon and then 6 hours later when it's right above your head.
Well, okay, the actual moon, yeah. But I have heard people argue that it's to do with some kind of optical, like, magnification equivalent of why we see, red sunsets and sunrises. The light coming through, the image coming through more of the Earth's atmosphere magnifies it in some way. Look, there's a really easy way to figure this out. How about you measure it? I'm assuming someone at some point in the history of the world has done that.
Yeah, and it's something you can do yourself, right?
Yeah.
Like you said, you can hold up your thumb at arm's length when the moon's on the horizon, and then a few hours later when it's above you, and you will see it's exactly the same size compared to your thumb. Or even when the moon is on the horizon, if you look at it through, say, a toilet roll, then suddenly it doesn't look so big anymore.
Ah, okay. If you strip out, what you're saying is if you strip out all of those external stimuli, all those other things that you can compare it with, and just look at the moon, then the psychological thing disappears. The illusion disappears.
Yeah, well, it's very, very interesting. So I looked into the moon illusion quite a lot, and I'm not a psychologist. I'm not a.
Is that what it's called? The moon illusion?
The moon illusion, yeah, and it's not. So I'm not an expert on these, but
Okay.
I kind of
Psychologists, write in and tell us, but don't blame Emily.
they do kind of make sense. So there's lots of reasons, and we're not 100% sure exactly why. The effect is real. The average person will see the moon on the full moon on the horizon to be about 50% bigger than they see it to be when it's at zenith, which is
Wow, I guess I wonder
directly above you.
how you'd measure. I guess you're just asking people, does it look bigger? How much bigger does it look? Yeah, okay.
Yeah, so it's about 50%. So the real reason is we're not really sure exactly the reason, but it's probably to do with a combination of a few things, shall we say. Now, the first thing to say is it's absolutely not to do with the amount of atmosphere you're looking
Okay,
through.
it's not a magnification effect.
No.
It's a visual illusion.
Yes.
Yeah.
So we know this, and actually it was Aristotle that put forward the atmosphere kind of
Oh, was it?
reason. Yeah.
Wow,
very,
going
very
back
long
that
time
far.
ago. And unfortunately, he's just wrong about that one.
I mean, I would have thought someone as brainy as Aristotle, because he had some good ideas, would have just done the whole measurement thing. Like, surely, isn't it better to do a measurement, an actual experiment, than to just come up with maybe it's this?
Yeah.
But someone else could just go measure it and go, no, Aristotle, you're an idiot. It's wrong. Look, measure the thing. Hold up your thumb. It's really, really easy. No, I have a theory. Weird.
But what is interesting, and that was kind of related, but it's not significant compared to the other things we're about to talk about, is that the atmosphere does change the color of the moon.
Oh, okay. Because of the whole sunset sunrise thing?
Yeah,
it's the same
yeah.
idea.
So you get a lot of refraction of the red light through the atmosphere of the Earth, which makes the sun look really, really red.
Mm-hmm.
If you get very dusty or very lots of particulate matter in the atmosphere,
You get amazing sunsets
really
and sunrises.
red moons, yeah.
And so the moon does the same thing.
the
Yeah.
harvest moon's very famous for this because lots of dust in the atmosphere.
Oh, okay. Is that where that comes from?
Yeah.
there you are.
And if there's a volcanic eruption, then often you see very red moons. So,
or bushfires,
Yeah.
or
or lunar eclipses, which is kind of exactly the opposite. So that's kind of when you're seeing the full moon.
Oh, yeah. That's the moon in the Earth's shadow.
Yeah.
Yeah. So it goes red then
Because you're looking at the sunlight that's passed through the Earth's atmosphere before it hits the moon.
Right. The only light remaining is the light that's gone through a lot of atmosphere, and so by definition, it's already red.
Yes.
And that's what comes back to us. Yeah. Okay. So other than that, there's no atmospheric stuff going on.
No,
It
although-
looks a different color, but it's not magnifying.
Some people have tried to argue that red things look bigger, but
But again, it's an illusion,
Yeah,
right? It's not actually bigger. I think that to me is the interesting thing, is that people are so adamant. I'm not mucking around here. It is bigger. You go and look at it. Hey, it's not.
so the reason is really to do with your brain. And I'm sorry, but your brain is not working very well when it comes to
Brains are pretty unreliable.
This
Brains and
particular
eyes
illusion.
put together, easy to fool.
very easy
really
to fool.
easy.
So if we look at the basic reason how we measure distance, right? And this is important because this is when we want to figure out how big an object is. We have this inbuilt tuition that we do to measure distances to objects. And for nearby objects, we can use parallax, which is the difference in the position of an object that's measured by your left eye and your right eye. And that gives you the depth perception, right?
Sure.
You can say, well, that's, the difference in your brain's converting that difference in the position of the object into a distance.
Yeah, classic one of those the other day. I was, again, on a car trip with one of my kids and she was noticing how out the window things close to the car whoosh past and things further away take much longer to go past the window. And she made that connection. It was a beautiful moment of intuitive science. She made the connection, but hang on, they're both going past the window at the same speed. It's got to do with the distance, the perception that we see them going past at different speeds. Yeah, that's parallax. That's how that works.
Yeah.
Things closer seem to go past our field of view faster. Really interesting. So you can use that to figure out how far away is this thing.
Yeah, to a limit.
Yeah.
And because eventually you get to things that are so distant that parallax, the space between your eyes isn't big enough.
Yeah, parallax just gives up and shrugs.
Yeah.
Yep.
And so the other thing that your brain does to figure out distances to objects is it says, well, I know how big a cup of coffee is.
Mm-hmm.
So if you put it quite far away and it looks very small, then I know that it's, if it looks small, then it's far away.
Yeah.
It's the whole Sesame Street, near and far, right?
Yeah. That's right. I remember that, and you can play with that in really, really good ways. I remember going to a museum of illusions and things once, where they had one of those crazy rooms where if you look at it from one viewpoint, it looks like a normal square box room, but the shape of the room is actually really weird. It's slanted away. It's playing with perspective, and so if you stand in one corner and then have someone else stand in the other corner, one of you looks like a giant and the other one of you looks tiny. But because of the perspective, the trick of perspective, your brain goes, well, I know what rooms look like. And so clearly the obvious answer is there's a giant and a not giant in this room.
Yeah. It's
We
fun,
can
isn't
fool
it?
each other,
It's really,
fool
really fun.
ourselves really easily. Brains
Yeah.
are stupid.
So mathematically, what our brains are actually doing is it's kind of a very simple way to look at it is we're saying what is the angular size of an object. So if you had a very long ruler and you measured from where the bottom of the object is with the ruler and you swept it up and you measured where the top of it was with the other end of the ruler, that would sweep an angle. Mm-hmm. So that's angular size. And then the length, the distance away from us. So you've got an angle and a distance.
Sure.
And that gives you the apparent size, right? Now, when we look at this illusion with the moon, we are playing with one of those things, and we're probably playing mostly with distance. Our brains are failing on the distance measurement.
Okay. So we're seeing it close to the horizon, but we're not only seeing the moon close to the horizon, we're seeing other things close to the horizon as well. And that's messing up.
Well, that's one part of the illusion.
Okay.
Okay. So let's play with this distance measure. So when you look at the moon, you're you don't maybe realize it, but you're making a judgment of how far away it is.
Okay.
Because you're saying, well, clearly it's not, in the next few meters away from me.
Yes,
because
it's not floating here just in front of me.
Yeah.
It's a long way away.
You know it's a long way away. But it's this, how far away it is relative to the horizon, to your straight above you, that's your brain is failing you on. Now, one reason why it might be doing that is the reason you mentioned. You've got foreground objects that you're comparing this to. So that means, and you use foreground objects or sort of intermediate steps to judge distance all the time. You say, well, I know that tree is about 50 meters away, so that thing that's smaller than that tree is going to be 100 meters away. The next tree is, smaller. This is your brain doing a very clever kind of, things are getting smaller, so they're getting further away. And we do this with clouds. So clouds that are right close to us are bigger and clouds that are further away from us. The problem is that these objects are confusing because we don't actually know the exact sizes of these things. And so we don't know the exact distances. So we just have kind of this broad kind of smaller things.
Sure.
And
our brain does a little sort of internal calculation and says, I think it's about this.
Which means we can overestimate the distance. So that means that we think that the distance is further than it should be.
Okay.
And we do this, and this is for the horizon, and we think that we live in a bit of a squashed world. So if you actually think about the human perception of the sky, let's say you've got this beautiful arc that moves through the sky. We actually perceive that arc to be, say, if you think about straight up, you think that the top of the earth is closer to you if you were to go straight up than if the edge of the earth if you go straight across.
Hang on. If we look straight up, then the sky, the night sky, seems to be just up there, not very far away. Whereas if we look out to the horizon, that seems to be a long way away. Is that what you're saying?
Yeah, it's a squashed sphere.
Right. So it's not a hemisphere dome where the top is as far away as the horizon. It's more of a sort of squashed bubble sitting above us, where the top is quite close and the sides are a long way away. Okay, I'd never thought about that, but yeah, you're right.
And this is, we see this with clouds. We actually sort of see the sky as almost being flat in our own perception, that the clouds on the horizon are kind of similar height to the clouds close to us.
Okay.
So this is called Emmett's Law, that we sort of have this weird perception. But what that means is that when we look at what we think the moon is when it's near the horizon, we think, oh, that moon's really far away.
Really far away.
Therefore, to be that size, it's got to be really
got to be
big.
huge. Look at the size of that moon. I mean, it's so far away, and yet, wow, it's really big. As opposed to directly above you where, well, it's just up there. I could basically touch it. That must be quite small.
Yeah.
Oh, dearie me, our brains are clever and yet stupid.
Yeah, so the moon appears closer, which makes it smaller, which is
Wow.
weird.
Yeah.
It's almost the reverse of what something
Because-
your brain should be doing.
Because it's the same size.
Yeah.
That's, oh my God. Okay, yes.
So that's a definite illusion, and that's probably a big part of the moon illusion. There's other bits as well that also are to do with distance. So one part is, like we said, these objects that we're doing these kind of jumping distances from one to another. And the third part is something called the Ponzo illusion.
Ponzo, I like that.
And this is, you can see some really nice examples of really like stick line drawings of ladders receding into the distance. The Ponzo illusion is about is that when you have converging lines, these make an object that's further away look larger than an object that's closer.
Okay.
And so we imagine that there might be some converging lines on the horizon. We kind of draw them in our brains. They might be coming from buildings or trees or whatever, but we're putting that, when you learn how to draw a perspective, you have all these, the vanishing point. It's this same kind of idea.
Yeah.
Your brain's
looking down a
drawing that.
road and it's wide near you and going down to a point right out at the horizon. It's vanishing down to a dot. That's perspective. That's what we learn, as you say. And that very thing that creates an illusion that makes things look bigger.
Yeah, further away.
Wow, that's the Ponzo illusion.
And architects have to deal with this kind of stuff all the time, right? Even the ancient Greeks and Romans had to, when they built columns in their pantheons and colosseums and things, they had to change the shapes and the size of them to back compensate for the fact that humans couldn't figure out this illusion.
Because if they built them properly, like the way you would expect to, it would look wrong.
Yeah.
Wow, I didn't know that. That's cool.
Yeah, it is quite cool.
Wow.
So again, we're overestimating the distance, which makes the moon look bigger.
Right.
So those are the reasons why your brain might be messing up the distance measurement. There's also some argument that your brain is messing up the angular size measurement as well. And I think this was also what you were referring to earlier, whereby if you see foreground objects, then the moon looks bigger than those objects. So you say, okay, there's a building there or a tree there. I have a very good understanding of how big a tree is, right? So the moon is bigger than that. So therefore it looks much bigger.
Yeah.
Whereas when you look at straight above you in the sky, you don't have anything to directly compare it to.
Yeah. It's weird psychology, isn't it?
Yeah.
Yeah.
And this is something called the Ebbinghaus illusion. So you can do this with very simple way by drawing a circle. If you draw two circles exactly the same size. If you surround one circle with circles that are smaller.
Oh, I've seen this, yes.
And the other circle with circles that are bigger, it changes the apparent size.
Changes the perception of the size of the original circle. Yeah. Okay, we'll put a few links to some of these illusions, because if you haven't checked out visual illusions, I saw a lecture a while ago by a guy at University of Sydney who just did an entire lecture where he was bending people's brains with visual illusions, and they really hurt. And that's a classic, absolute cracker. Really good. Wow, I hadn't thought about that before, but you're right. That's probably got to do with it.
So overall, it's probably some combination of all of the above, and maybe the combination is different for different individuals depending on how you learn depth perception.
Yeah.
But
they all point in the same direction,
give
which
us
is
the same outcome.
Yeah. So I think we can conclusively say then that A, the moon is not bigger when it's closer to the horizon than when it's above us. B, our brains are very, very clever at fooling themselves. Yeah.
Yeah. And I think a good place to kind of wrap it all up is a quote that comes from Kant, actually. This is in the 1780s, so they were very aware about the moon illusion at the time. He says, "The astronomer cannot prevent himself from seeing the moon larger at its rising than the same time afterwards, although he is not deceived by this illusion."
Right. Well, that brings us to the very end of this incredibly moonful episode. That's a new word.
No mooning involved.
No mooning. Not allowed on this family-friendly podcast. Very moonful episode of the Syzygy podcast. I've learnt a lot. I didn't learn a hell of a lot about supermoons. I mean, it is what it is.
There's a limited amount that you can learn, I think.
But we went off in directions I really didn't think we were going to go. So thank you very much for that, Emily. You've done a heck of a lot of research, as ever, on something which is not your primary research focus, I think it's fair to say.
But I'm happy to be interviewed for all of your upcoming moon questions.
Yes, if you want Emily on your particular radio program to talk about the next crazy rat moon or whatever the hell it's going to be coming up in August, then give her a bell. She'd love to take your call. If you want to get in touch with us for any other reason, there are a load of different ways that you can do that. Emily, how do people do that?
So we are at Syzygy Pod. And I missed a trick with this episode, honestly, because we had so many Syzygys. Every full moon is a Syzygy.
Oh, I didn't even bring the bell.
I mean, we could have gone crazy.
I got to apologise to Circus Stew because I don't have the bell with me. Right, that's it. Need to bring the bell in for next time. Yeah, you're right. Loads of Syzygys.
So SYZYGY Pod. That's our Twitter handle, and you can find similar social media accounts across Facebook. We've got on Instagram.
Yeah, as previously mentioned, we're not on TikTok. I don't think we're ever going to be on TikTok or Snap2Chat or whatever the hell it's called. But yes, we have a website as well, syzygy.fm, where you can find all the past episodes and show notes and pretty pickies and all of that sort of thing. And a contact form where you can get in touch with us to say hi. If you'd like to support the show, a bunch of different ways you can do that. The number one way is to just share it around. Tell people that you think would be really excited about moons. If anyone's ever come up to you and said, "No, I swear to you the moon is bigger near the horizon," point them at episode 60 of the Syzygy podcast and then get them to go back and listen to the previous 59. If you want to support us financially, go to patreon.com or patreon.com and become a patron of the show. Sling a few dollars our way to help us keep the lights on and the electrons flowing through the website so that we can keep doing fabulous astronomy stuff every week. Having said that, we'll be back in about a week with more fabulous astronomy stuff. So until then, see you later, Emily.
Catch you later.
Bye, everybody.